Hi there, this is Katie with TutorPug, and today I wanted to talk a little bit about business pre-calculus and this concept of limits. And especially you guys are going to start out with the limits of something called rational functions. And there's a lot of vocab involved with limits in general. There's a lot of vocab involved with math. There's vocab involved in any language, there's vocab involved in sailing, there's vocab involved in sports. So a lot of times you can't do the activity until you know what we're talking about. So when we talk about a rational function, typically we're talking about, if we want to get really fancy, we're talking about a ratio of a polynomial over a polynomial. Well, right now you can mostly think of it as some kind of equation over some kind of other equation. And the thing that's really important is that the denominator contains variables. It contains x's. So all of these are, for your purposes, they can be considered rational functions. Denominator has a variable. Denominator has variables. Denominator has variables. Denominator has variables. Denominator has so forth and so on. So when you're dealing with a rational function that is specifically a polynomial over a polynomial, all right? What's a polynomial? A polynomial has variables raised to numbers, so x's raised to numbers, whereas non-polynomials have numbers raised to x's. So if we come back over here, both of these are polynomials because it's the variables that have exponents. The variables have exponents. The variables have exponents. The variables have exponents. Down here, the number is the base and the variable is the exponent. So these two on the bottom are slightly different animals, but we're gonna figure out how to find the limit no matter what. So first of all, if we have a polynomial function, to determine the limit, you're going to compare the degree of the function on the top, or what's in the numerator, to the degree of the function on the bottom, which is the denominator. All right, now we gotta know what degree is. Okay, degree, the degree of a polynomial is the biggest exponent on a variable. So for this numerator, the degree is 2. For this numerator, the degree is 1, because that x has an invisible 1. The degree of the denominator is 2. Here, the degree of the numerator is 2, because that's the biggest exponent I see on a variable. The degree of the denominator is 3. All right, so once you compare these degrees, if you're going to compare two things to each other in terms of size, 3 things can happen. Either the top is bigger, or the bottom is bigger, or they're the same. So these are 3 rules that you are going to have to memorize. You just have to learn them. I'm sorry, there's a few things in math that you just have to memorize. So if the degree of the top is bigger than the degree of the bottom, and you're assessing the limit as we go to infinity, that limit is infinity. It means that we're going to go up forever and ever and ever. If the degree of the bottom is bigger than the degree of the top, the limit is 0. It's a rule. You memorize it. And if the degree of the top is equal to the degree of the bottom, then the limit is what we call the ratio of the leading coefficients. Well, what does that mean? Here we go, more vocab again. If I have this equation, the degree of the numerator is the biggest exponent, so it's 3. That means this guy's numerical dance partner would be the leading coefficient of the top. And in the bottom, let's make this be a 9. The degree of the bottom would be 9 because that's the biggest exponent, and the leading coefficient would be that shot caller's numerical dance partner, which is -3. So if we have a situation where the degree of the top equals the degree of the bottom, we're going to take the leading coefficient in the top divided by the leading coefficient in the bottom, and that is the limit. So here, let's do a few little quick examples. Every single time, we're going to compare, and then I'll show you a calculator trick. Degree of the top, I'll get a different colored pen. The degree of the top is 1. If you don't see an exponent, it's an invisible 1. The degree of the bottom is 1. So if we think about our scenario, the degree of the top equals the degree of the bottom. So we're going to take the leading coefficient of the top, which is 5, divided by the leading coefficient of the bottom, which is -6. So this guy's limit is 5 over -6. And we're done. It's the number. We found it. Move on. Come back down here, polynomial over a polynomial. We do our same test. The degree of the top is 2. And so the leading coefficient is -9. The degree of the bottom is 2. The leading coefficient is 12. Degree matches degree. So our limit is -9 over 12, which is -3/4. And we're done. Degree of the top, that's 1. Degree of the bottom, biggest exponent on a variable, that's 2. 2 is bigger than 1. So the degree of the bottom is bigger than the top. The limit of this is 0. Now, I want to show you a quick calculator trick on this guy that goes hand in hand with another way of thinking about the limit. If I wanted to figure out the limit of this as x gets bigger and bigger and bigger and bigger and bigger, I'm going to put this guy into y1. So I'll come over here. That's a fraction. Try to get both of them here on the screen. This is a fraction, so on the newer operating systems, I can hit the green alpha button and the y equals button. And if I select n/d, that stands for numerator denominator, and it gives me a little skeleton fraction. So I can just enter this without having to worry about parentheses. 16x squared plus 9. Bump down to the bottom, 5x minus 3. So I've got that in, and now I want to assess, I want to make the calculator do the hard work. What happens to this whole thing? What y value is it headed towards as the x's get bigger and bigger and bigger? Well, okay, let's go to our table, which is second and the graph button. See how right above graph it says table in blue? So if you hit the blue button and the graph button, we get this table, which means I can enter what I want for the x variable, my input variable, and the calculator will do the math and spit out what that calculation is. So I'm going to make x approach infinity, which just means get bigger and bigger. I start at 10 and 100 and 1,000 and 10,000, and I'm just going to keep tacking on zeros because I'm looking for this pattern. I'm looking for the general approach. And we start out at 0.85345, then we go to 0.80405, then they're going to change, but it looks like as my x variable gets bigger and bigger, my output is getting closer to 0.8. So I could, if I completely went into vapor lock, I could consider this 0.8, but let me show you how this works if you don't have a calculator. There's a lot more calculus that goes into this, but the short version is if I take the square root of that whole first term, that gives me 4x. The square root of 16 is 4. The square root of x squared is x. And I really don't have to worry about this guy because I'm kind of doing some funny math here, but it's okay to get me through for these purposes, especially for this particular class. Now I can compare the degree of the top, which is 1, to the degree of the bottom, which is 1, and that means I take the ratio of the leading coefficients, which is 4/5, and 4/5 happens to be 0.8. So that one worked out nicely, and you might see one of those coming up on a free response option. If we move right along, the limit, we have a polynomial over a polynomial, compare, compare. The bottom, the degree of the bottom is bigger than the degree of the top, so this limit is 0. Now, here and here, we have a little bit different animal. And I'm gonna show you how to do them on the calculator just to kind of get your brain warmed up. So if I put this guy into the calculator, I have 14.5 over 0.25 plus 3 to the x. And I'm going to do that same thing, go to the table, and I'm going to make x get bigger and bigger and bigger and bigger. And as this x gets bigger and bigger and bigger and bigger, this language here on my calculator, 2.5 e to the negative 4, is the calculator's way of saying 2.5 times 10 to the negative 4th. So that's a pretty small number. It's a decimal point, 3 zeros, 0.25. The next guy in line says 3 times 10 to the negative 47, which is an even tinier number. And then by the time I get up to 1,000 and 10,000 and 100,000, the calculator just spits back an error. And what that means is that for this problem, as this x gets bigger and bigger and bigger and bigger and bigger, this whole thing is gonna disappear to 0. So then you look at this and you're like, oh, okay, same structure. I have a number. I have something on the bottom where I have a number raised to a variable. It must be 0. This is where we have to be careful because the value of this number that has that exponent on it is going to change the behavior. So if we take this guy and go put him into our calculator, I've got 17 over 0.5 plus 0.65 to the x, and then I do my 10, 100, 1,000 game. Notice how it looks like as the x's get bigger, the y values are getting closer to 34. So these y values, this whole limit is headed towards 34. So here's what's happening. If you go back to your calculator and you do 17 divided by 0.5, 17 divided by 0.5, that's 34, and that's not an accident. So here's the take-home message. If you have this structure, if you have this animal, and the guy with the variable exponent is bigger than 1, that whole limit, as x gets bigger, is going to disappear. If you're taking the limit as x gets bigger, and this animal, if the base is less than 1, 0.65 is less than 1, as x gets bigger, this piece is going to turn into 0, and 17 divided by that number is going to be your limit. So there's a few tricks, there's a few tips, there's a few things you need to memorize. Go study real hard, have fun,